Well, I'm very pleased to introduce Professor Frederick Dreyer. He's the Professor Emeritus of, in the Department of Mechanical and Aerospace Engineering in Princeton University. He had his degree from Princeton and worked as a faculty member since 1981. So he has over 40 years of academic career, contributing many areas, especially on the combustion and fuel utilization, including combustion kinetics, alternative fuels, droplet combustion, and fire science, and more. And also recently he has conducted successfully the MURI program as a PI on science-based design of fuel-flexible chemical propulsion energy systems. And he is currently a fellow of the ASME and Society of Automotive Engineers. And he received numerous awards, but I will not list all of them, just one award, the most prestigious Edgerton Gold Medal Award in 2012. So I will not spend more time to give him more time to share with you his perspective and knowledge. And Fred.
Thank you very much. Thank you to the Combustion Institute for inviting me to make this presentation today. It's different than presentations I've made in the past, in that being 70, I can now say what's really on my mind. And if you find parts of the presentation provocative, they're meant to be. I'm attempting to start a discourse amongst us that are interested in fundamental science and those that need our science today to make things happen that we want to see in 2100. I'm most appreciative of the many friends that have decided to sit down front because they've influenced my life and my interests. But I wanted to acknowledge several people specifically. Clearly Irv, for having really inspired my interests in an academic career, which I had no intent of doing when I came to Princeton. My wife will tell you that we were going to leave in a year and a half with a master's degree. And my interest in applications-driven basic research. That's something that Irv instilled and nurtured and has become a major part of my life for most of my career. Charlie Westbrook, clearly his friendship from the early 70s when we first collaboratively introduced comprehensive chemical kinetic modeling aspects certainly has been a mainstay in many of my thoughts. Thank you, Charlie. Alicia Ronzi and Rolf Reitz have contributed immensely through discussions and their recent publications that are only appearing now this month in helping me form some of my thoughts. And most appreciatively are some of the people who I've worked with closely at Princeton. Marcus Chias, Steve Dooley, Tanvir Farouk, Sang Hee Wan, Mac Haas, Jeff Santner. Each and every one of them have contributed to the discussions and the thoughts that I'll show you today. And finally, to those who have supported my research over that period. You'll notice, like me, some of the corporations that are listed here have disappeared. They've been absorbed by others, but Mobile Research Corporation and Ethel Corporation were certainly very important in me forming my thoughts. So let me start today by first showing you something that John Hayward put together in 1981 about the energy field. and engines and fuels, which is what I want to speak about today. I'm not going to talk as much about kinetics as many in this audience would think I would. I want to talk about real fuels and their interface with engines, all types of engines and all types of fuels. And I think John was quite insightful 32 years ago to build this slide. And you'll notice that we should be well into alternative fuels by this time because petroleum should be disappearing by now. This isn't as good as it might seem from the point of view that there are some things that are missing. This is how much the evolution of engines has changed in 30 years. HCCI and RCCI engines were not really being discussed 30 years ago, and they're now extremely prominent for their possibilities of major changes in thermal efficiency in engines and major changes in the way we deal with pollutant emissions from engines. The second aspect is biorefining. We've been learning much about how to make things in very efficient ways from plant life. And we in this audience have been very interested in fuels, but the real aspects that are most profitable are not fuels. They're chemicals and biochemicals and pharmaceuticals. And on the list, fuels is not at the top of those. And to make fuels economic is going to be a real challenge. So the question marks are real for our future because I wanted to make sure all of us realize whatever we say now probably is not going to be what really happens. We're going to evolve new science and new technologies. Well, the drivers 32 years ago are the ones that I've listed here at the top. I can remember very well in 1981 the issue about energy security. It was exactly the same here in the States, but there's something very new. It's called carbon particulate emissions and climate change. We were talking about global cooling in 1976, not global warming. It was a very different time. And today, the paradigm we hear is replace fossil fuels, get rid of fossil fuels, go to a sustainable future in energy, don't use carbon as a hydrogen and energy carrier. We'll make fuels from biomass. We'll make solar fuels from solar energy, water, and atmospheric CO2. We'll use renewable energy from wind and solar and sea and geothermal, and we'll replace having to burn fossil fuels. We'll use hydrogen as a carrier. We don't need carbon. We'll make electric vehicles. There's been much innovative science here this week, very new. Our models are evolving. Our understandings in these areas are evolving at a pace probably not seen before because of the coupling of computations and experiments. Now, I'm going to emphasize experiments today because I think experiments are the proof. Models are a way of interpreting experiments, and unfortunately, models are still evolving, and it's going to take some time, I think, years, before we have all of the details that we really wish. And we have to do something in the interim. Those science things are expected, especially for the alternative fuels field. This is only a very quick representation of what's emerged in less than 10 years of different methodologies of producing various fuels through mainly either thermal processing or bioprocessing, and not so much by actually combining them in terms of optimizing these processes. But we need to think about how to integrate those things. And I want to remind you all of a message that my mentor delivered in 2000, which was transformative, close-coupled, use-inspired basic research is even more important as technology transfers and communication issues evolve And it's more important today than it was 15 years ago, in my opinion. But we have to look at today's stage. Kelgatki reminded us yesterday that there's going to be 2.5 billion vehicles on the road by 2050. There are 15,000 aircraft in the air today globally, and expected 40,000 by 2032. The retirement age of aircraft today is at 23.5 years, and it's been between 25 and 27 years for the last 3 decades. Think about trying to replace that inertia in vehicles, with new technology, with controlled emissions. When we send our cars here that have some control someplace else in the world and they remain in the pool for another 30 years. Our pool will change, their pool will not. Petroleum, 87 million barrels a day today, going to 115 million barrels a day by 2040. US and EU, we're both forging ahead with very aggressive programs for alternative fuels. The rest of the world, I doubt seriously. My opinion is they can't keep up with us if we do this. And it's reminiscent of the issue I mentioned next, which is the alternative liquids issue in 2040 is only supposed to be perhaps maybe 4.6 million barrels a day. And a very large share of that not coming from biomass, but from coal and shale and other petroleum fossil resources. China and India's growth in energy is going to outpace the rest of the entire world over this period. You cannot ask people to make transfer to non-fossil fuels when people's living standards and their ability to eat are affected. And this is no different than it's been for the last century. So major evolutions are going to be required, but we have to be careful about the inertia of the energy system and the transportation system, that we actually integrate these changes now, or we cannot build these things in an economic manner that they will be self-sustaining. We can't start an industry of alternative fuels that is going to affect 2100 if we don't integrate it now. And that means those fuels are not going to be things we burn in pure state. In my opinion, pure state discussions about oxygenated fuels are very important to science, but they're not going to solve the application side, because all of those are going to require that we blend those materials with petroleum-derived materials if we're going to incubate this new industry well. So that seamless integration is important. The seamless integration doesn't just extend to the use side, but to the processing and distribution side as well. Do you think that we can add new pumps at every station for new fuels, or change our distribution system immensely? We need to consider how to do this in as much a seamless way is important. The important issue here too is that we need engineering tools to do this. They can't be DNS, they can't be something that takes 100 or 200 hours on computers. I need to do something parametrically. I need to change a parameter. I need to see what the optimization of those issues are. And that means I must simplify each one of the submodels that are involved in those engineering design tools. I have yet to see someone tell me which ones I can achieve the least accuracy in and still have good engineering tools. And each one of them is going to be different. Many of us in this audience are interested in chemistry, and I'll remind us all at the end, how accurate do we need to be for engineering tools? I'm not sure. It's a question. So let me say first now, these tools, we want to know how to represent real fuels and the addition of other compounds to it. So I wanted to show you a real fuel. This is a GC by GC analysis of a real diesel fuel, recently published. And each one of those little circles is an indication of the component mass in that exposure. And you'll notice the carbon number scale up at the top and the type of fuel here on the right. And we want to be able to represent that in engineering design tools. You can see how complicated this is. It's not only complicated in terms of the amounts, but the distributions. There's thousands of compounds here, and we need to represent those in engineering tools. So how do we do this? Well, this is the commercial way of doing it as far as the industry is concerned, and it's going to stay. Why is that? Because when we make fuels, we have to have a way of classifying them and standardizing them so that they can do this. They are fit for purpose in the particular design system that we wish to use them. To do that, how are we going to specify that? When we really need to do that, we specify it through what are called indicators. Fuel indicator references is what I've termed them. Research octane number, motor octane number, cetane, several types of cetane, cetane index, derived cetane number. Are they all the same? No, they're not. Cetane index is something that you and me should not be using because it doesn't apply to alternative fuels. It doesn't apply. It's built on correlations from petroleum. Distillation curve, viscosity, density, initial boiling point, T10, T50, T90. Those are recovery temperatures for distillation. I've recovered 50% of the mass at T50. Smoke point. Odd test, right? Odd test. A wick test for smoke point. A height of a diffusion flame that soots. It's a standard for gas turbine fuels. Oxygenate contents. We never define what the species distribution is in these fuels. We only define limits in reality. And that's the connector between the left side and the right side. And I purposefully added another engine class here called LTC, low temperature combustion. And I'm going to talk specifically about HCCI and RCCI. Now, yesterday, how many of you feel comfortable about engines? How many of you feel you know how a MON and RON is interpreted? I'm going to go very quickly here because I don't have a lot of time for this, but I want to make sure we're all on the same page on these issues. It's my instructional heritage from teaching. This is a spark ignition engine, and we know very well that this peak in pressure in the chamber has to be properly positioned in terms of where the piston is, or we don't get optimal performance. And we change that by changing when we ignite it with a spark. But we also don't want the unburned charge to ignite here in front of that propagating flame. And the MON-RON test define that under different RPMs and different inlet temperatures. And the compression that results in that auto-ignition and engine knockdown here on the bottom is a function of the compression from the cylinder, the compression of the end gas from the flame propagating, and the low temperature and intermediate temperature chemistry that's going on in the end gas. So it's a very complicated process. And I get out of that a RON and MON by taking a primary reference fuel of N-octane and isooctane and N-heptane and mixing it so it gets that same parameter. I got to match flame speed, auto-ignition chemistry. Okay. Very complicated indicator, right? Very complicated. And that's what Dr. Kalgotky was talking about yesterday. RON and MON and octane index and how these things just don't seem to work for some other applications because of the differences in RPM and other issues. And I want to talk some more about that. Diesels. Multi-phase combustion. Here I was pre-mixed because I put fuel in the chamber very early during the compression stroke, perhaps with port injection. Okay? Here I'm injecting directly into the engine, and I now have a diffusion flame, and the heat release here is not controlled by that burning rate progress across the chamber as it was in HCCI or in spark ignition. It's controlled by the mixing rate in the system. But it's controlled by the mixing rate. And I have two stages to it. When I start injection at SOI, and right here, this is top dead center now for the piston, I have some time for things to mix, so I have a pre-mixed burn of stratified material when it first ignites, followed by a mixing limited one, and these can vary depending on the design, and we have some very modern types of injectors today that can pulse several times during this issue to change that whole profile. But here's the complication. Diffusion flame, very hot, NOx, not hot enough, particulates, because they didn't burn out, NOx particulate trade-off. I've got to have all of this after treatment to control emissions. It's as expensive as the engine. If I can get rid of it, it's extremely important. Homogeneous charge compression ignition, LTC, a very specific kind. I'm going to homogeneously charge the engine with a mixture. There's no flame propagation in this engine. The burning rate is controlled completely by the chemical kinetics. This is the theory. The reality is it's not. If I stratify the charge, I get some other behaviors that are important. But I want to show you some things that are very important to the issue of OI and MON and RON. When I look in this engine under a condition where it's controlled auto ignition for a homogeneous charge, I see what you see over here on the right as a function of crank angle. Crank angle here, if I can read it against the light, is going to be specified where 0 is top dead center. And what I've done in this, what they've done in this experiment is to adjust systems such that this peak heat release is in the right place to get performance. They do that by finding the right crank angle, CA50, where 50% of the heat release has occurred. That's a control parameter for these kinds of engines. And I want to show you what happens. I've got some low temperature heat release out here. And I've got the major heat release here. These are for primary reference fuel mixtures. Remember, and heptane has an octane number 0. Isooctane has an octane number of 100 in PRFs in the mixture. And you'll notice the heat release out here, which is called a high temperature heat release, is changing, the low temperature heat release changing, and there's an intermediate temperature heat release that's changing. And I'm trying to model that by using octane index and RON and MON. Do they have any time history similar to this? None whatsoever. And this is a big complication, and there have been lots of challenges recently to whether octane index and K factors are the right way to judge HCCI. Can I really optimize? Because I need to know these, because where that heat release is an integral function of those other heat releases. Well, let me show you that those heat releases are associated directly with chemistry in these systems. These are reactivity profiles from the flow reactor at Princeton. I've mixed two fuels. Downstream, I'm going to sample them, the same fuel mixture, the same flow residence time in the system, and all I'm going to do is change the initial temperature. And what I see is low temperature chemistry at first, and notice the PRF 0 is very active. N-heptane, I have a lot of it. Isooctane, I have none of it. And I start mixing isooctane and N-heptane, and suddenly I'm getting very big changes in the LTC, the LTHR of this mixture. And if I happen to do it for toluene, I don't see any LTHR. And if I mix toluene with a PRF 87, that's 87% isooctane, 13% N-heptane mixed with 21% toluene, you can see I suppress the low temperature heat release, and I also changed the intermediate temperature heat release. Where is it here? It's here, right there. This profile is CO plus CO2, and right there is about 90% CO. I haven't burned it yet. Why not? The temperature is too low. I have no chemical branching. in this system from H plus O2. So this is yet to enter high temperature chemistry and HTHR, which is associated with CO oxidation. This is CO oxidation. This is the LTHR, that's the low temperature chemistry, and right here is hot ignition and is causing the ITHR issue. So what is the answer to emulating real gasolines? What several have found is that if I try to emulate a real gasoline by using a PRF mixture that matches the MON and RON, it doesn't work. Why doesn't it work? It doesn't work because those aren't the only parameters that are important to emulating real gasoline. And this paper by Pera and Knopp demonstrates something that we started working on in 2000. And you'll find the early publications around 2003, 2004 about matching what we call property targets for gasoline. And they chose the following property targets: RON, MON, HC ratio, and if it had an oxygenate in it, OC ratio. And they said, I've got to match those things. You can't do that with PRF. The HC ratio for PRF near 90 is 2.5. And the gasoline is 1.8. That means the energy density of those materials are entirely different. That means that an air-fuel interface, I don't have the right volumetric stoichiometry with air for phi equals 1, which is the way I need to operate an engine to control with three-way catalysts. So let's try to match those, and we'll do it by adding toluene to N-heptane isooctane, which is what they did. Here's the gasoline that's used for standards in Europe. And here is a match of that gasoline in terms of RON, MON, HC ratio, and I left out the oxygen first. I'm not going to put an oxygenate in it. And here is the density and the lower heating value that were obtained by doing that. And when I did that, I got exactly the performance of the real gasoline in a compression auto-ignition engine. And not only did I get that, I got the same emissions. So we can match gasolines, but we can't match gasolines with just OI. There are more combustion property targets that are needed to match and study real gasolines. And you cannot study real gasolines in real engines using PRFs. How many of us have been using PRFs all of this time to try to understand real gasoline? You can't do that. And you certainly can't do it in HCCI because I can't match the LTHR, the ITHR, and the HTHR. I said some of my statements are provocative, and I meant it. And I hope we have a discourse about these things. I think it's very important. So is this idea really something I can pursue elsewhere? Suppose I try and I inject two fuels now, one that has a high octane, one that has a low octane, and I do this in real time so I can vary the octane character in the engine. Reaction control, compression ignition. Two fuels on board. Oh my goodness, two fuels on board. 2 tanks in every diesel on the market today to control NOx. Did you know that? Urea is injected after the engine. That's a second tank to control NOx in vehicles. So 2-tank technology is there. How about injectors? Injectors are there, PZTs. Controlled, very multiple pulse. I can stratify the charge in this HCCI by direct injection and by aspiration of one fuel and injection of another. I can do it several ways. And this is what Dr. Reitz has been studying and Sandia has been studying. The thermal efficiencies of these engines have been demonstrated in the laboratory to be higher than 60%. That's 35% better than the best diesel. And they have very little after treatment. I don't need to treat for NOx. I don't need to treat for particulates because the temperatures are so low in these engines. And the increase in thermal efficiency isn't magic. It's that the heat losses to the walls in that engine are so much lower because the combustion temperatures are so much lower. So this is the future for combustion. It's completely compatible with today's fuel system. I can drive up to a pump and fill it up partly with gasoline, partly with diesel fuel. I can modify diesel and gasoline to meet the advanced diesel engine design and the advanced spark ignition engine design. And I don't care what their octane numbers are because I'm going to build a smart engine. I said I was trying to be provocative, and I am. I think this is going to affect the diesel-gasoline split that we heard of yesterday that's diesel-dominated. And I don't need a third fuel stream of an intermediate cetane number fuel to do this. I can do this on any of these engines. So it's seamless. I want to change topics now. Can I go to gas turbines? Very different topic, very different kind of design. Can I use the same combustion property targets? Well, here, smoke point is an important issue for knowing emissions in gas turbines. So I'm going to add smoke point to this system, but I wanted to just show you very quickly there's two very different concepts going forth in gas turbines. And it has to do a lot with how I atomize and how I distribute in the beginning. This is not as well characterized right now as is diesel injection, and it's a hard part of initialization for modeling gas turbines. Here I'm going to have a rich region. I'm going to try to keep it rich to keep the temperature down. I'm going to quench, then I'm going to put things together and go to a lean premix system over here, and you can see they're very different. So let's talk a little bit about these property targets. DCN. There is no auto-ignition property for gas turbines. I'm going to make one up. I'm going to use the diesel one. It's not an auto-ignition property. It's a reactivity property. I'm just going to substitute it. It's only a correlative property. I'm not going to use it as a diesel. I'm going to look at HC. I'm going to look at molecular weight, which was very important in the last case, and I'm going to add TSI, which is a representation of the smoke point divided by the molecular weight. And I want to emphasize something here. I'm not interested in the real fuels that we started with. I'm interested in the distinct chemical functionalities that they produce. What are those? Well, if it's an N-alkane, I produce lots of olefinic fragments that are straight chain. If it's an isoalkane, what do I produce? Isoalkanyl groups, C3s, C4s. They have a very different history in terms of their reaction than the straight chain olefins. Aromatics, what's the biggest thing that I could possibly see? Benzyl groups. Benzyl groups, different distinct functionalities. Are there more of them? I believe so. Do we have them all identified? No, this is a work in progress. But they control this region here of C4s to C1s, which generate the pool, which attack the real fuel, and it's this entire cycle that defines the burning rate. Does it work? Here's a comparison of simple surrogates of N-decane, isooctane, and toluene, or N-decane and isooctane and two other aromatics. And all I did was match the property targets that I mentioned with each of those. A first generation, which were only the ternary components, and a second generation. What's different about them? The second generation can actually match the molecular weight. The first generation couldn't. And if I look down at the bottom, you can see the reactivity type profiles I showed you for the flow reactor are reproduced for the real Jet A fuel and the surrogate mixtures nearly identically. Not quite in this region, and I'll talk about that. But at the low temperature region, they're identical. At the high temperature region, they're identical. And here's the proof of that in terms of ignition delays of the real fuel and the two surrogates. The data spread in these are as tight as one will ever see in systems. There's rapid compression machine data here, both generated by parts of the Muri team that did this work. And finally, on the right, we looked at strained extinction in diffusion flames. And there we see the molecular weight is a very important issue. And we can talk about that later if you wish. Speciation. I want to mention Ken Brzezinski. This is his work in pulse shock tubes. And what he's done is look at the way this thing speciates as a function of reaction temperature at about the same residence times. And you can see that the real fuel and the second generation fuel, totally different in their real species distributions, look identical except for a couple of things, and I'm going to show you what those are. In C2s, they look identical. 4 components and 1,000. They don't look identical in butenes. Why not? Because we know isooctane produces T-butyl radicals. And we're using that as the isomer here. But it didn't matter at the C2 level. So emissions can be done this way, and you have to be careful how detailed you wish to know something. That's the same thing that's true with anyone's detailed model. What does this all come from? Simple functional group analysis of this problem. We chose to represent CH2, CH3, and benzyl groups just as a first cut for functional groups here. And we made up our first generation and second generation mixtures that look exactly like that fuel. And we made up 6 more C2 second generation mixtures. You can see the 5 of them down here at the bottom. They're all different in their compositions, but they have the same combustion property targets. And look at the distribution of CH2, CH3, and benzyl groups. It's telling us that functional group or carbon-carbon bonding structure in these molecules is a controlling factor. Well, I want to show you some new data. This hasn't been published yet. It's about to be. It's reactivity profiles for C7 through C16 alkanes, N-alkanes. And you can see as we go to larger and larger alkanes here, this is C7, this is C16, more activity in the low temperature region. And look at what the hot ignition, where peroxide decomposition controls, did. It stayed exactly in the same place. And over here, you can see as well that the CO mole fraction is also showing exactly that same behavior. There's a blow up here that you, I hope, can see. I can't see it very well up here. But I want to put you on this figure. This is the formaldehyde that's formed in those systems. Look how good the formaldehyde is as a marker of where LTHR is and ITHR is. This has been thought about in the literature. This is the best experimental evidence for this I have seen. And I want to point to the right figure over here. This is a correlation of the cetane number of those fuels with the temperature rise that's only about 9 degrees over all of those reactivity profiles. And you can see it's entirely linear. Oh, I can't even measure 9 degrees accurately. We know that in premixed ignition, in strain premixed ignition too. We can't measure as accurately as what we see. But what's more interesting is the correlation down below, the water formation with this issue. That I can measure very accurately, and that's coming from RH plus OH, which is one of the main heat release reactions in this system. So, wow. This is published in 1987 by DeFries and Indritz. And you can see here a correlation of cetane number with the normal chain length for paraffins and the normal side chain length for alkyl benzenes. And you can see that these are very well correlated with functional structure. And he was one of the first groups to introduce nuclear magnetic resonance to define functional structures and carbon-carbon bonding and correlate just about every kind of physical parameter you can think of with chemical structure. So I want to show you something about ignition delays. These are computations. And what I wanted to do was take methane, hydrogen, C7, C16, N-alkanes, and C16 isoalkane and compare the ignition delays. Where did fuel disappear in each of those? Turns out in hydrogen and in methane, there's 95% of the fuel or more left when ignition occurs in this plot. How much fuel is left when ignition occurs with the hydrocarbons? None. None. It's all been converted to fragments at that point. And that maximum heat release that we use to measure ignition delays here is carbon monoxide burning that has been suppressed by all of the fragments of hydrocarbons because CO plus OH can't compete with it. Is this new knowledge? Irv Glassman published this in 1978 in terms of experiments on hydrocarbons. So this isn't new knowledge. It's not something we discovered from models. It's something I'm trying to show you as important models. What does toluene look like here? Does it look like the N-alkanes, or does it look like hydrogen and methane? It looks like hydrogen and methane, because hydrogen, methane, and toluene ignition delays are controlled by getting the first radical in these systems. The others are controlled not by getting the first radical at all. So what happens to the olefinic structures in these systems? They're different with pressure and temperature for each one of these. And I haven't yet added an aromatic to these. And if I add an aromatic to these, they'll differ immensely because the aromatic will burn late. It will compete for radicals for the N-alkanes, and so it'll slow the N-alkane oxidation, but it will also itself not regenerate radicals, as does the fragments from the N-alkane. Not only does the olefinic evolution change with the initial temperature and the fuel, but its distribution changes, C2s to C4s. And these are the things we want to couple with at detailed chemistry level. Let me show you what happens when I add an alkane. I take an alkane and I add aromaticity to it. I have three different aromatics here, 1,3,5, 1,2,4, and N-propylbenzene. And on the left, you see what their reactivity profiles look like, and you can see as individual pure components, they're all different when they start to react. But when on the right, when I add them to N-decane, they all affect the N-decane oxidation the same. Why is that? They're competing for the N-alkyl radical. They're competing for the radicals that are producing the N-alkyl groups. So OH, HO2, CH3. And they're competing very heavily for it, and that's their main effect in low temperature chemistry is competition and not regeneration of radicals. Well, let's use a little bit what we know. In the 2007 papers on diesel surrogates, we recommended to use N-desylbenzene as one of the components we wanted to use for diesel fuels. So it's very high boiling points, very difficult to make experiments. So let's see if we can represent it by N-propylbenzene plus N-heptane, or or N-butylbenzene and N-heptane. There's an entire paper representing this, but the DCNs don't look anything like the DCN for N-desylbenzene. And I can go back and show you the value for that in the DeFries study for carbon 10 chain length from an aromatic group. You can't represent this without going to N-hexadecane with N-propylbenzene, and that is because the groupings of CH2, the adjacent CH2s in those molecules, is another distinct functionality for high cetane numbers. So if I want to do things, I've got to know a lot more about the functional structure. And you can see on the left that the ignition delay for this mixture computed is very different than anything of these two, which match each other, by the way, because their DCNs are so close. Well, this is what we're really interested in. We don't care about homogeneous combustion. We want to be able to model full multi-component combustion. So now we've got to couple the liquid phase injection, its penetration, its atomization, its vaporization, its mixing with chemistry in our engineering tools. And I've used the schematics here from the work at Sandia. I think they're wonderful for those purposes because they show how complicated this problem is and what we have to try to put into engineering design tools to learn how to add anything to petroleum. So let me show you something else. Would you believe that I can blend up to 6 to 10 refinery streams, measure online NMR spectra of them, and control the resulting MON and RON to 0.32 units? That's done commonly today. Our community doesn't know, I think they don't know, how powerful NMR is. What I'm showing you here on the right is what John Edwards has produced in terms of linear analysis of the spectra for NMR, and he can produce these characteristics from the NMR spectrum of a real fuel to ASTM standard levels. I never did an ASTM standard test at all to characterize this gasoline. I notice I'm not only getting RON and MON, I'm getting physical properties, density, distillation curve, lower heating value. These are all chemical structural properties of the fuel. And if I have the right property-property relationships, I can predict them just the way I predict everything else that you and I are so used to in using chemical thermodynamics and flame propagation in the subjects we study. There are people trying to do QSPR fitting of laminar flame speeds at tailor-made fuels from biomass in Germany. So this is a very powerful tool put together with the GC type, two-dimensional GC type of analyses that I showed you earlier. We can characterize these fields really well, and we don't want to reproduce their compositions. We never have. The most prevalent way to do a surrogate for a real fuel is to choose one species for a class function of molecules. And what I've shown you so far is the class function doesn't matter. What matters is the functional group representation. So let's go a little bit further. This is Mueller et al.'s paper in 2012 where they did a carbon atom NMR analysis of their fuel, and they tried to reproduce it. Where's the catch? They had to choose on the right side what the surrogate components were that they were going to use to match it. How did they do that? I don't know. We play with these things right now. We don't have good theory. I don't have good theory yet. This is applied science necessities for what I described earlier. This is a very good example. If we can understand this, we can make up fuels, and they did, by doing this, made up fuels that not only had the same chemical indicators of cetane number, it had the same physical properties within those errors. So I didn't have to separate physical properties and auto-ignition properties at all to get the fuel right, which is what we've tried to do with models. And the models, I'm afraid, just aren't precise enough yet to do that. They're wonderful for interpreting the results, but they're not precise enough to understand whether this theory works or not. So let me show you that it doesn't work at the class function level. On the right are two of the diesel fuels that they tried to represent by this surrogate, and you'll see that the class functions of aromatics, alkanes don't match at all what was in the real fuel. It's that that combination matched the appropriate functional group distribution. Functional groups may be a way of developing much simpler chemical kinetic representations of fuels. That's my message. So this is where we are now for developing mechanisms, and what's frightening to me is this looks linear and linear on a log-log scale, but this is what we've generated since 2010. The numbers of reactions are growing faster, and we want to be down here for engineering design, and we think we can get there by numerical reduction methods. My opinion is we can't. We can't get that small. Numerical reduction methods are telling us something else. How much of the model is just not relevant to the engineering global combustion properties we're interested in? That's a horrible statement to say. I apologize. But it's true. It said they weren't relevant. Their accuracies were not relevant. Their uncertainties were not relevant. Well, we eliminated them, but why did we put them there? Because we want to learn science. It's important for us to learn science. We need to know how these things work. But it isn't going to help us with this part of the problem. So what would? Example, Ralph Reitz's work. He is putting together physical models for the fuel this way. He takes classes of species. You can see there's a very large library here to match the distillation properties. Do you want to build a detailed chemical model to represent this chemically? That's what's called physico-chemical surrogate development. The same species are going to represent both the physical properties and the chemical properties, and I've given up on it. That's what preparing this plenary did for me. We have to do it the way Ralph is doing it, and it says something about what we need to know in basic science in order to do it. So physical properties, I've got all the library here for every physical property I could think of here. He uses that, but then he connects it to the kinetics this way. The left side is physical properties, the right side is chemical kinetics, and what he's done is he's tried to choose a specific species that represents a class of chemistry for the fuel components on the left. Class detailed modeling. Gosh, we've been doing that a long time. And it works, doesn't it? There's nuances. We need to know the nuances. But this is a workable way. It's completely flexible. I can add oxygenates on the left or the right as functional groups. I know how to put new alternative fuels into petroleum. Ralph is actually doing full engine experiments with this, both for gasolines and diesel fuels, and he's converting what he knows in diesel fuels to gasoline species through the derived cetane number, octane number correlations. Oh my goodness, they correlate exactly. Now, if I hadn't shown you those engine schematics in the beginning, and I told you that they correlated exactly, you probably wouldn't be surprised. But look what went into those two different determinations. Flame propagation for Mon and Ron. No flame propagation in DCNs. Vaporization, mixing. And they correlate exactly. And I showed you that the functional parameters correlate exactly with NMR. They're chemically representative of the real fuel. Those are the relationships we need to understand. I'm not here to tell you I understand them all. I'm here to give you the message that there's lots of work to be done in real fundamental basic science that is directed specifically to getting where we want to be in 2100 with a lot larger reduction in carbon emissions and new fuels. And this is the way it's probably going to occur. We'll build a C0 to C4 model that's as accurate as we can make it, and we know it's going to continue to evolve. Why? We don't know all of the mechanistic parts, much less the parameters in it. Half of this meeting is about new mechanistic discoveries. Important. So no model that's published today will remain the model tomorrow. I'm absolutely convinced of that after 45 years of working on hydrogen oxygen. Okay, so let's think about a hydrocarbon. It's going to change. We need that change. We need to understand that. But we also need to reflect to the engineers what they can use. So we can build all of these other submodels around it. This is what Alicia Ronzi does. He was very nice to share this figure with me. I want to invite you to look at this paper that's quoted down at the bottom. It just appeared in IJCK. There are lumped kinetic models for almost every kind of real fuel you can think of. And he was nice enough in that publication, after I sent him the reactivity profiles I showed you earlier for 4658 Jet A, to do the 2 surrogate fuel mixtures a priori for that result. And you can see that they agree exactly with the experimental data, and they have, recall the experimental data did not fit the real fuel in the intermediate temperature region just above the hot ignition. It was too slow. That is a result of cycloalkanes. It's the only place cycloalkanes have any effect on global combustion properties. We're trying to get that into the literature. I'm sorry it was rejected here. So I don't have any more privilege than you do. And we're still working on it because a reviewer doesn't understand that I'm not interested in the detailed issues first. I want to get to what the global issues are. This is going to be important to what? ITHR. Intermediate temperature heat release are affected by cycloalkanes. So if I want to know that in gasoline issues, I'm going to have to include them as one of the surrogates. Olefinic species, they act just like isomer structures. Weakly branched alkanes, I'm raising that only because there is a big difference between trying to represent real fuels and following 2,3-methylheptane. Why? 2,3-methylheptane generates a pool of radicals that are controlled entirely by the initial molecular structure. When I do a real fuel, here's the saving grace. There are thousands of molecular structures, and they span the entire region of weakly branched isomers. I don't need to do that one. I can represent it by a strongly branched isomer. So if we have a family of strongly branched isomers, we can have class kinetics for them. We certainly can have class kinetics for N-alkanes, and those are the 2 backbones of all petroleum-derived fuels. So there's some messages here about how to do this. I want to say one last thing here. On the left, you see the distribution of viscosity of real jet fuels. And you can see how much the viscosity varies of a real jet fuel, even though we've put it in a fit-for-purpose specification. I want to show you the right because that whole variation in the fuel property is encompassed in very small changes in the temperature of the fuel at the atomizer. Where's the coupling in a gas turbine between atomization and combustion zone? It's in heat feedback to the atomizer. That is going to change the atomization process, the droplet penetration, the droplet vaporization, and it's radiatively affected in gas turbines. That's why there's a control through smoke point measurements of radiation in gas turbines. We don't care about the emissions from that. We care about the radiative feedback to the liner and to the atomizer so that fuels don't coke. But could we use it as an emission issue? I believe we can. We've just published a paper on making up surrogate mixtures from fluids, not single components, but fluid cuts and real fuels. So we'll mix real fuels and fluid cuts from solvents, and we'll make those 4 property targets agree with another fuel, and they have exactly the same global combustion characters. Why is that important? I can make up fuels that have very different physical properties that way and all have exactly the same pre-vaporized combustion chemistry. I can do the experiments now in real turbulence, in real systems at pressure, and from the parameter space, identify which is important. I think I'm close. I'm sorry. I'm that close. I've told you a lot of things today. I hope the message was provoking. It was meant to be. I hope it's not the kind of provocation that we go away and say, I don't want to listen, I don't want to argue, I don't want to discuss. This was a provocation to discuss. because our community is on a cusp of something that's very important. We are doing immensely important science. I would not want to ask how many industrial representatives are here. And it's because they don't see, and we don't see, the complete connection of what we're doing to what they need to know. And this is where our community is going to live or die, in my opinion, over the next 2 decades. We have to be relevant. We are relevant in science. There's no question. But we have to be relevant at the industrial level in solving this problem and producing this seamless integration of what we want to accomplish in reducing carbon emissions, eventually facing loss of fossil energies, and I mean eventual. I'm a very big believer that we've got to find the right technologies for carbon capture and sequestration. We don't have them yet, but they're all important to us maintaining living standards and other issues. So I'm going to let you read my conclusions. Thank you again for your time. I really appreciate it. I hope it was interesting.
We thank Fred for a great lecture, and I'm presenting the certificate to him now, and please, after that, don't run off. Thank you.
Thank you so much.
Here you go.
Thank you so much for inviting me. Thank you.
I'm particularly happy it has my signature.
Thank you again.
So I will keep you a couple of moments longer, and it may seem a little strange that I would like to give you some farewell remarks already today, because we still have a number of lectures and posters, etc., etc. So this is not meant to discourage you from attending all those. It's just that when we have the farewell reception tonight at the plaza, there will be no microphone, there will be no opportunity to speak to you. So I will take just a few moments to, well, express the hope that you had a great conference. And I hope we had, thank you. I hope that this is also an expression of quality, but I'll give you some quantity and statistics to scare a soul. So we had, as you've seen, a nice video with nice remarks from people that weren't pre-selected, and that is part of the outreach and media strategy that the committee under Margaret Wooldridge will drive further. We had almost 1,600 technical participants here. We had about 450 papers and 1,200 submissions. We had 700 posters. There are still a lot to see. There were about 650 people at the Young Researchers Mixer on Monday, and you heard it here, it was really favorable in some people's opinions. We are going to continue that. There were about 750 at the awards banquet, and there were about 1,050 attendees on the boat yesterday with some spectacular moments. So if you feel like I do, you're full of new ideas, you have met new people, and you have seen some wonderful surroundings. But above all, if you feel like I am, you will be a little bit tired. After the rush of having everything prepared before the symposium, having discussed and presented your work here, listened to others, and hopefully after some good after-work activities. If you feel like I do, you would say, well, probably maybe enough by tonight, okay? Time for something different, time to go on, time maybe even for some vacation. The old saying is, you should stop when things are best, okay? Now, in this sense, there's only one remaining thing for me to do, and that is pass on a great big number of thank yous. So, first of all, I would like to thank the local organizing committee for the tireless work and great organization in a memorable location. Let's give them a hand. My great and special thanks go to the program chairs, Thierry and Sukho, and their numerous colloquium co-chairs and people who worked with them, the poster committee, and all who worked on the scientific program to make this a wonderful location to be the meeting network for combustion science. So give Thierry, Sukho, and all Matthias Ehme, and all who worked on the scientific program another big round of applause. I would like to express my thanks to all the students that were involved in helping during the conference. Your work was very much appreciated. Thank you. This is also maybe the spot where I could thank all those who were meeting with their committees and who were meeting with their satellite meetings and their new incumbent satellite meetings at this conference. It may be looked upon as an additional burden to have all these conferences, but I think we should look upon them as this is where the growth is. So I'm happy that all these patterns evolve, and we'll see more of that in Seoul and in Ireland, I suppose. So let's thank them all. I've already thanked those in the Combustion Institute office who did a lot of work you didn't see, and I think we don't need to clap the hands again because Barb already had to go to some family member things. I don't think a wedding in her direct family, but she's no longer here. But I would like to thank especially another group. That's the young researchers from around the world who came here, because it's you who make us understand the needs for the future with your work. While all have presented the science here, we put a special hope on you. So being a combustion scientist or engineer in a world of transforming energy systems is a challenge, but it's also an obligation. Please contribute with your work to make combustion more efficient and cleaner in the future. See you in Seoul.